realm of digital communication, the persistent spectre of noise invariably corrupts the fidelity of transmitted information. Achieving reliable and accurate transmission is a fundamental challenge, demanding sophisticated techniques to combat these impairments. A watershed moment in addressing this hurdle arrived in 1967 with Andrew Viterbi's seminal paper, Error Bounds for Convolutional Codes, and an Asymptotically Optimum decoding algorithm. This work presented a revolutionary solution to the problem of efficient decoding algorithms for convolutional codes, especially in noisy environments. Viterbi's contribution was the introduction of an efficient decoding algorithm, now universally known as the Viterbi algorithm, which achieves maximum likelihood decoding for convolutional codes. The paper's central claim revolves around the Viterbi algorithm's optimality. It asserts the algorithm's capacity to achieve performance approaching the theoretical limits of reliable communication. These limits had previously been established by Claude Shannon in his groundbreaking work on channel capacity. Shannon's insights, particularly concerning the relationship between channel capacity, signal-to-noise ratio, and the maximum rate at which information can be transmitted reliably, provided the essential theoretical framework for Viterbi's work. Shannon's work, however, did not provide practical methods for achieving these limits. Viterbi's algorithm, in contrast, offered a concrete, implementable solution. Viterbi's work plunges directly into the core of the challenge, the derivation of error bounds, and the precise mathematical formulation of the algorithm itself. The algorithm offers a dynamic programming solution to the complex task of decoding convolutional codes. The computational complexity, a crucial factor that could render a decoding algorithm impractical, is handled elegantly through the algorithms. The work's foundational elements center on convolutional codes, a class of error-correcting codes where each encoded symbol depends upon the current input symbols and a finite number of previous input symbols. The paper shows that for a given convolutional code, the probability of decoding an error can be demonstrably bounded above by a function of the code's parameters. The algorithm explores the trellis diagram, a graphical representation of the states of the convolutional encoder over time. The paper demonstrates that the most likely path through the trellis, representing the original transmitted data, can be found efficiently. This is achieved by calculating path metrics, a cumulative measure of the likelihood of the received sequence given a particular path through the trellis. The algorithm systematically searches the trellis, discarding less likely paths and retaining only the most promising ones. The paper's significance extends beyond the realm of information theory. The Viterbi algorithm achieves practical, efficient decoding, which is crucial for a variety of digital communication systems. The legacy of Viterbi's algorithm reverberates across diverse fields. It continues to be a cornerstone of modern digital communication systems. Its principles underpin technologies in deep learning, and the very algorithm now finds applications in bioinformatics, showcasing its enduring impact. The algorithm's design is a testament to its adaptability, demonstrating its ability to solve complex problems in a variety of contexts. The genesis of Andrew Viterbi's 1967 paper, Error Bounds for Convolutional Codes and an Asymptotically Optimum decoding algorithm, arose from the pressing need for reliable communication in noisy environments. The work directly addressed the limitations of existing decoding methods, particularly for convolutional codes, which encoded data by sliding a window across the information stream. Prior to Viterbi's work, decoding these codes was computationally intensive, often involving exhaustive searches through all possible code sequences. The paper sought to provide a computationally efficient decoding method that would simultaneously achieve optimal or near-optimal performance. The core of Viterbi's contribution resides in its algorithm. This algorithm, a marvel of dynamic programming, decodes convolutional codes efficiently. The algorithm is structured around a trellis, a graphical representation of all possible states the encoder can occupy over time. Each point in the trellis corresponds to a specific state, and the transitions between states represent the encoding process. The algorithm assigns a branch metric to each transition, representing the likelihood of receiving that particular data given that transmission. The paper's central feature is the calculation of path metrics. A path metric is the cumulative sum of branch metrics along a path through the trellis. The Viterbi algorithm then systematically searches for the path with the highest path metric, the path that is most likely to have been transmitted. This approach, a dramatic departure from brute force methods, drastically reduces computational complexity. The paper's detailed steps proceed as follows. First, construct the trellis diagram based on the convolutional encoder's structure. Second, calculate the branch metrics, typically using the Hamming distance or a similar metric. Third, begin decoding at the starting state, calculating the path metric for each path. Fourth, at each state, retain the path with the highest path metric. This is known as the survivor path. Fifth, continue this process through the trellis. Sixth, at the end of the received sequence, the path with the highest path metric represents the decoded data. The work highlights how using dynamic programming facilitates the pruning of unlikely paths, focusing computational resources on the most probable sequences. The foundation for the error bounds, presented in the paper, rests on the concept of the probability of error. The work derives upper bounds on the probability of error for certain parameters of the convolutional codes. These parameters include the constraint length, the rate of the code, and also the noise characteristics of the communication channel. Central to the error analysis are the transfer function of the code, a mathematical representation that captures the number of paths of a certain Hamming weight, and the minimum free distance, the smallest Hamming distance between any two valid code words. The analysis then establishes a relationship between the code parameters and error performance. The paper provides a tight upper bound on the error probability, showing the effectiveness of the Viterbi algorithm in achieving close to optimal decoding performance. The paper also includes several specific equations and inequalities. One key inequality involves the probability of error, denoted as P sub e, being upper-bounded by a function of the code's distance properties and the channel's noise characteristics. Another key equation is the transfer function for the convolutional code. This transfer function helps determine the code's error performance. A concrete example presented in Viterbi's paper is the application of the algorithm to a specific convolutional code. This demonstrates its ability to correct errors. The paper showcases how the algorithm can decode received sequences, even in the presence of noise, thereby recovering the original information. The simulation results illustrated how the algorithm performed under various channel conditions, confirming its theoretical predictions. The examples provide tangible evidence of the algorithm's practical effectiveness. The immediate impact of the Viterbi algorithm was most keenly felt in space communication. The ability to efficiently decode convolutional codes was a breakthrough. Reliable communication over vast distances in such noisy environments became possible. It enabled the success of missions like the Mariner program, allowing the transmission of high-quality images and scientific data from distant planets. The algorithm has since experienced wide adoption and expansion in fields that rely on reliable digital communication. The algorithm is now a cornerstone of digital cellular systems, which include numerous modern communications systems, such as the Global System for Mobile Communications, GSM, and Code Division Multiple Access, CDMA. The algorithm also serves as a core component in data storage systems and other applications. The algorithm's foundational principles continue to inform research in error-correcting codes and also inspire new decoding algorithms. In addition, the algorithm has found uses in fields outside of communication. The principles adopted by the algorithm were adopted by speech recognition algorithms, which require reliable processing of noisy data. The algorithm's concepts, such as dynamic programming and trellis-based decoding, also inform bioinformatics, used to align DNA sequence. The Viterbi algorithm influenced other researchers. The algorithm provided a foundation for research in decoding algorithms and error-correcting codes. It inspired the development of more advanced decoding techniques. Moreover, the algorithm has influenced fields like hidden Markov models, which are an extension of the trellis-based decoding from the Viterbi algorithm. The enduring legacy of the Viterbi algorithm lies in its capacity to transform the reliability of digital communication and its broad impact on various fields, especially those that require data processing. The algorithm provides an ingenious solution to decode convolutional codes. Its ability to efficiently find the most likely path has spurred innovation over many domains. The algorithm stands as a monument to the power of dynamic programming. The principles of the Viterbi algorithm continue to inspire new decoding techniques and find applications in ever-expanding areas, establishing its place in information theory.